Welcome back. So this is the last section in the normal distribution. We're looking here at sums of random variables. So we'll require some results here from the last section. The first thing is I've got x is normal mu x sigma squared x, and y is normal mu y sigma squared y. I'm going to put w as the sum. With x plus y here, then w is going to be normal distribution. Again, we know that. The mean will be something that I'm going to work out, and the variance will be something I'll work out here. The first thing is, with a plus there, the means will simply add. With a minus, the means will subtract. The variance we know, sigma squared w, the variance of x plus y is variance of x plus variance of y. There's a plus there, plus twice the covariance. With the minus there, the minus sign appears here. So be careful. In this, the plus sign is between the variances. The minus, if there's a minus here, is going to be the covariance. And the further result is if x and y are independent, and then we know covariance is 0. So independence simplifies things quite a bit. In that case, the means simply add, and the variances simply add. And I've still got back a normal distribution. And of course, I can take this not just to 2, but to several normal distributions. So the result I've got here is if x1, x2 up till xn are independent normal distributions, the means are mu I and the variance is xi. Variance is a sigma I squared. If I add the x's to give me another random variable y, then the y's also have a normal distribution. The means simply add, and the variances simply add. And there's a special result for independent random variables. If independence isn't there, it's more complicated because I've also got to take care of the covariance term. So have a look at this slide carefully, understand what's going on here. All I'm doing is adding my random variables. So that gives me the sum of means as the new mean, and the sum of variances as the new variance. What I insisted here about independence. Example over here. Suppose the income of executives is normally distributed with incomes of men and women independent of each other, and the means and standard deviations are in tens of thousands of dollars. For men are 20, which makes that's 200,000, and the standard deviation here is 2.5, that makes it 25. For women is 15, which is 150,000, and then here 20,000. So the question here is, what's the probability that a randomly chosen female executive earns more than a randomly chosen male executive? So I'll first of all let F equal income of female, and I'm being a little bit loose with notation, but that's fine. And M equal income of male. Then what I know is F is normal, the female, the mean is 15, and the standard deviation is 2, so I went 2 squared there. And for males, it's again normal, the mean is 20, and the variance is 2.5 squared. So what I'm after here is probability that a female executive earns more than a male executive. So what I'm going to do here is I'll subtract this to make it as f minus m is bigger than 0. And now I've got a random variable that's f minus m. I can call that d. And I can find its distribution. So then I've reduced this to a problem of just saying d bigger than 0. Let's see how this works then. So I'm going to put here d equals female minus male. So the mean of d is simply the means subtracted. Yeah. So mean of the female is 15. Male has mean 20, that's negative 5. And the variance of d, just checking here, independence holds. So variance of d is the variance of the female, and this is where I require care. I require variance here, so it's 2 squared plus 2.5 squared That's 4 plus 6.25, 10.25. So D is also a normal distribution. The mean is -5 and the variance is 10.25. So what I wanted was probability that the female earns more than the male. And that's the same as saying that female minus male is bigger than 0. And I can now replace that by simply saying D is bigger than 0. And I'll do the usual stuff, which is standardize this so it becomes probability Z is bigger than, be careful, it's 0 minus -5. So I'm bracketing it to make sure that I have the two minuses here. And I want the square root of 10.25 because I'm dealing here with the variance. Be careful. In this case, the variances add, not the standard deviations. The variances add. So if I work out this number here, and this is 0 minus -5, that becomes 5 on the top of a square root of 10.25. I can use R for this. So I got 5 divided by square root of 10.25, and I get 1.56. It's positive because I've got two negatives here in a row. So I'm looking at probability of Z being bigger than 1.56. So this part here from tables 1.56 comes to, there's 1.5 there, and 6 is across here, 0.4406. So the bit I want is 0.5 minus that. Zero 0.0084. Not many, but less than 1% in fact. Alright. Part B says, find the probability that an executive couple has a combined income of more than 400,000. So now I want probability that female plus male is bigger than, now this was in tens of thousands, so that'll be bigger than 40. Now again, I'm going to put here T equals F plus M. So T will be a normal distribution. The means will add. So the means, if I go back to check, were 20 and 15, 20 and 15. The means will add. So that's going to be 20 and 15 is 35. And the variances will also add. And that becomes 10.25 as before. So just to make sure here, the mean of T is the mean of F plus the mean of M. So the means here add. So this is 15 plus 20, which is 35. And the variance of T. Here again the variances will add because I've got independence. And so that's where I get my 4 plus 6.25. So what I'm after is the combined income of more than 40,000, because these things are in tens of thousands. What that becomes is probability that T is bigger than 40. Be careful of that. So replace the f plus m by t. And so the usual story, I standardize this, I get z is bigger than 40 minus the mean is 35 over the root of 10.25. So the number here is again 5 over 10.25, so this is the same as what I had before there. This still comes to 1.56. In other words, it's exactly the same as before. And so the answer I had before, my 0.0084, is still what I get here. So you can see how this works. It's not that difficult. I've got sums and differences. Here's another example. This is more difficult. A machine makes washers with hole diameters that are normally distributed with mean 15.2 millimeters and variance 0.03 millimeters squared. Another machine makes bolts, diameters again normal, with mean 15 and variance 0.01. So you can see the washers, remember those things that is like that, and the bolts like that. And the idea is the bolt will fit in the washer. So the washer is actually a disc like that with a hole in the middle. And we can see that the mean of the bolt is less than the mean of the washer, so most will fit in. Question here is, what's the probability that a randomly selected bolt will fit through a randomly selected washer? So again, I'll define myself random variables. So B equals bolt diameter and washer W equals the washer diameter. So then I need the distributions, and each of them is normal. So the bolt diameters are normal. The mean is 15 and the variance is 0.01, and the washer is again normal. The mean is 15.2 and the variance is 0.03. First part says that a randomly selected bolt fits through a randomly selected washer. So what I want is, if the bolt is to fit through the washer, the diameter of the bolt must be less than the diameter of the washer. So that means I want probability of B less than W or B minus W less than 0. So I'm looking here at B minus W. So I'm going to put D as B minus W. And so D will have a normal distribution. The difference in the means from B to W, B minus W here is negative 0.2. And the variances add, so that's 0.04. So I just formalize that, put the difference as B minus W. So D has a normal distribution. The mean is negative 0.2 and the variance is 0.04. So again, the problem reduces from involving two random variables to just one. So probability of B minus W less than 0 becomes probability of D less than 0. And so that again I standardize, so I get Z less than negative, too fast. So it's 0 minus the mean, which is negative 0.2, be careful, over the standard deviation, which is the root of 0.04. So if you work out the numbers here, that's 0.2 and the bottom is also 0.2. So this is probability of Z less than 1. And you can look up tables now. You can do this kind of stuff. It comes to 8413. In other words, about 84% of the balls in the washers, pick them at random, they will fit each other. Now the next part is, what should the mean diameter of the washer holes be if 99% of the bolts are to fit the washers? So now the washer was what I'm looking at. So the washers now have some normal distribution with mean mu, but the variance is as before, so that's still 0.03. And the bolts haven't changed, they're still normal. The mean of the bolts was 15 and 0.01. So the problem doesn't change much at all. So again, now what I'm after is essentially the difference here is still washer minus bolt. Now, if you go back a little, I did bolt minus washer there, so I'll be consistent in that sense. Let me change that. It doesn't matter the order, it's just that the way you write probabilities then changes. So it's going to be bolt minus washer, and D has a normal distribution. The mean is the bolt minus the washer, so it's 15 minus mu. And the variance is still 0.04 as before. What I want is, now I want 99% of them to fit. So that means D less than 0 is 0.99. In other words, if I standardize this, I get Z is less than 0 minus, the mean is 15 minus mu over 0.04 square root of, and that should be 0.99. So if I just draw myself my normal distribution table, what I'm looking at here, my normal distribution graph, I want a probability of 0.99 on the left hand side. This whole thing shows 0.99. So the tail here is 0.01. And as I said before, these critical values are listed separately. If I go to my normal table and I look up at the bottom, the 0.01, I saw this before, this is 2.326. This is 0.01 in the tail, the value is 2.326. So that means this value here is 2.326. In other words, if I work this out, this is 0 minus 15 minus mu. So it's negative 15 minus mu. This is 0.2 when I take the square root. That should be 2.326. So I have to solve for mu from here. So I multiply this 0.2 across and then take the negative sign across as well. And if you work this out carefully, what you'll get is negative 15 plus mu is 2.2 times 2.326. And so the mu will work out to be 15 plus and again I can use R for this. Zero 0.2 times 2.326 plus 15, and I get 15.4652. So I've changed the mean of the washers from 15.2 to 15.4. Now that might not seem a very large change, but what will happen is, of course, now you've changed the washer diameter, you will find the bolts won't fit so snugly anymore. And that's a problem. So just in general speaking here, if I want more of the washers to actually fit the balls, I would reduce the variance to make sure there's less variation there. Generally speaking, I improve quality by looking at variation, not the mean. Now finally here, critical values, as we were seeing earlier, are listed at the bottom of the table. And so we saw earlier what you'll get is an example over here, probability of z bigger than z is 0.01. So the tables give us that straight away. 0.01 there is 2.326. Next one is z less than z is 0.05. So that's on the left hand side. We know that on the right hand side I'm going to get 1.645. Left hand side simply makes it negative 1.645. In absolute value, if I want 0.05, well, all that means here is if I've got 0.05 in absolute value, I've got half on each side. So the half here is 0.025, and the other half here is 0.025. And so the z value I get from the tables here, if I look up 0.025, 1.96, that number there is a very useful number, as you'll see. So this gives me 1.96. And likewise, 0.01 means that I'm looking up half on this side, 0.005, and half on this side, 0.005. And if I look up the tables for 0.005, I'll get 2.576 over there. And that finishes our discussion of normal distribution. Thank you.